Faraday's law. Faraday's law. You spin me right round, baby. Faraday was a British chemist and physicist who contributed to the study of electromagnetism and electrochemistry. Faraday was born on the 22nd of September in 1791 in South London. He's from a poor family and had a basic education. At 14, Faraday became a book apprentice. Over the next 7 years, he educated himself to read. By 1821, he published a paper. In 1831, he discovered electromagnetic induction, the principle behind electric transformers. He then passed away in 1867, having contributed a hell of a lot to science. Here we have Faraday's original experiment. What Faraday did was he passed a magnet through end turns of a coil of wires. The field in the copper conductors forced the free electrons to move, which induced a current. This caused him to create his famous equation. We have here a coil of 2,000 turns of 0.196 meters and a diameter of 0.09 meter. And what I'm going to do is I'm going to drop the bar magnet. And this induces the current in the free electrons. On the original experiment, Faraday would have used a flux meter, but as we can see, this one here is broken, but the needle moves around a lot, which would have been quite hard to measure. Now we can computer analyse what we have here, putting it on a time scale and measuring it and outputting graphs, reducing the error compared to what Faraday would have had to deal with mathematically by hand.
If the magnetic flux through a surface changes, an electric field is induced along the boundary of that surface. If a conducting material is present along that boundary, the induced electric field provides an EMF that drives a current through the material. The law can be shown in two forms. The integral around a closed path C of the electric field dotted with the incremental segment of path C, which is dl. The dot product means that it will be the sum of the electric field lines parallel to dl. And that is equal to the negative of the rate of change of magnetic flux through any surface bounded by C. The negative sign comes from Lenz's law, which states the current induced by the changing magnetic flux always flow in the direction so as to oppose the change in flux. The normal electric field lines originate on positive charges and terminate on negative charges. However, in induced electric fields, these form complete loops around the boundary. The second form is the differential form. This shows that the curl of the electric field, where the curl is a measure of the field's tendency to circulate about a point, is equal to the negative of the rate of change of the magnetic field with time.
Here we have modern applications of Faraday's law. This includes DC motors, electric generators, induction stoves, and electric transformers. This also includes electric guitars.
The electric guitar has a pickup. This is a magnet surrounded by a coil. When the strings oscillate, the magnetic field is cut and changes the magnetic flux. This induces the electric field, producing a voltage which drives the current, the voltage passing the amplifier, and then produces the sound. Here we have taken the pickup out of the guitar. First, using a piece of wood shows no voltage is produced. This is because insulators are not a ferromagnetic material. However, using a magnet, which resembles the physical properties of guitar strings, a voltage is induced, which is displayed on the screen of the oscilloscope. We aren't able to make the magnet oscillate with a frequency as large as a guitar string, which is why the oscilloscope doesn't show a continuous waveform.
Alright, so what we have here is a guitar hooked up to the oscilloscope, and so we can clearly see that when I plug the string, we see the changes in voltage. So from this we can determine the changes in magnetic flux, make the changes in voltage, and then when this voltage passes through the amplifier, we get a sound. And this is how your parents used to make metal, kids.
Faraday's law!